Before we dive into today's content, I'd like to give credit to Professor Rampton Zand, PhD from the University of South Carolina, for the slides we'll be discussing. Today we are going to discuss the MIPS processor. You might wonder why MIPS. Here's why. Comprehensibility. MIPS is designed in a way that it offers real tangible CPU system that we can fully grasp within a single academic semester. Think of it as system that's detailed yet easy enough to understand within a short span of time. Applications of MIPS. MIPS isn't just something we study, it's used in everyday tech. It powers devices like Cisco routers, many Android devices, even our HD TVs and cable boxes. Even if you've ever owned or played on a Sony portable PlayStation, guess what? It has multiple MIPS processors inside. Simplicity. MIPS is known for its simplicity. It's not overly complex, making it easier to learn and understand. What's cool is that MIPS shares a lot of similarities with ARM, another major type of processor. In fact, MIPS was an inspiration for ARM. So, if you get to know MIPS, you're directly or indirectly getting acquainted with ARM too. Open architecture. MIPS was born in the academic world. Its design and structure are open for all to study and understand, promoting transparency and knowledge sharing. Resources. There's a wealth of free software tools and online resources available for MIPS, making it user friendly for learners and developers alike. Designed for the future, MIPS is ideal for Internet of Things and portable devices. For those unfamiliar, Internet of Things refers to interconnected devices that can collect and exchange data. Think smart devices like smart thermostats, wearable health devices, and connected cars. In the image, you can see MIPS creator CI40 Dave board. The development board showcases the capabilities of MIPS processor. The board has various components like connectivity options, storage, more, indicating its versatile application. Uh, let's dive into a concept called design abstraction. Imagine you are building a multi-story house. Each floor has one specific purpose, like kitchen on one and bedrooms on another. Similarly, when designing computers, engineers don't lump everything together. They use layers. What is design abstraction? It's a technique where hardware and software designers organize their design into different levels or layers. Just like our house, for example. Why use it? Computers at core understand very basic instructions. Think of these as the building blocks like bricks for our house. However, the software we use every day is more complex, like the entire floor or the room of our house. How does it work? Now, to bridge the gap between our sophisticated software and the basic computer language, there are layers in between. These layers takes the complex tasks we give them and translate them into simpler instructions that the computer and hardware can understand. Now look at the diagram. The innermost circle labeled hardware is like the foundation of our house, is the physical part of the computer. The middle circle, system software, acts as an interpreter. instruction from software and translates them into a language the hardware can understand. You can think of this as plumbing and electrical wiring that makes our house foundational. The outermost circle, application software, represents the programs and the apps we use daily, like our favorite game or word processor. This is like the decor and the furniture of the house, the parts we interact with directly. In essence, design abstraction ensures that our intricate software works seamlessly with basic foundational hardware of the computer. The slide showcases the journey of a program from high level language, which is more readable and human friendly, to a format that computer can directly execute. High level program language. This is a simple function written in high level programming language like C or C++. It is designed to swap the value in an array v at index k with the value of k plus 1. Think of this as a recipe written in plain English. It's easy for us humans to understand. Compiler. A compiler takes this high level code and translates it into assembly level language specific to the computer's architecture. In this case, it's MIPS assembly language. Imagine you need to explain the recipe to someone who speaks in a different language. MIPS assembly language. The assembly language is a low level representation of the code that is closer to the machine language but still somewhat readable by humans. It uses symbolic names and numbers to represent operations and data. Assembler. The assembler takes the assembly code and translates it into binary machine code. Binary machine code. This is the final format that a computer understands and can execute directly. It consists of only zeros and ones. Essentially, the slide demonstrates the transformation process of a code from a human friendly format to a computer executable format. It's about making the computer understand what we want it to do. Five classic components of a computer system. These components describe the fundamental parts that work together or make a computer function. Input. This refers to devices or methods used to feed data into a computer system. Examples are keyboard, mice, touchscreen, and cameras. Output. These are devices or methods used to present data from a computer system to a user or another system. Examples include monitors, printers, and speakers. Memory. It is the storage area where data and instructions are held temporarily, like RAM, or permanently, like a hard drive or SSD. It allows the processor to fetch and store data as needed. Data path. This is a part of the CPU's processor that performs arithmetic and logical operations on the data. Think of it as the workhorse that does the actual computation. Control. This component directs the operation of the processor. It tells the data path what operation to perform based on the instructions that the CPU is currently executing. The visual representation. The image portrays the relationship between these components. The processor CPU is the heart of the system, handling the data and the instructions. It's made up of the data path, where the data is processed, and the control, which directs the operations. Memory is shown adjacent to the processor, emphasizing its role in the providing the CPU with data and instructions. Input and output are shown as external components interacting with rest of the system. The slide also emphasizes that a processor or CPU is essentially made up of data path and control. However, the processor by itself does not make a complete computer. A computer requires all the other components like memory, input, and output devices to function as a cohesive unit. So, in essence, this slide provides an overview of the foundational elements of a computer system and how they interact with one another. This slide presents the concept of the von Neumann architecture, which is a fundamental design architecture for most digital computers. Von Neumann architecture's central theme, the design is based on the storage of instructions in the memory along with the data upon which these instructions operate. Main components are the CPU microprocessor. It is the brain of the computer where most calculations occur. Memory, dynamic random access memory, a type of computer memory that can be accessed randomly and is volatile. So that means the data is lost when the power is turned off. Key points: CPU and memory location. Both are located on the motherboard. Assembly language execution. The CPU executes one assembly language instruction at a time. Assembly language is a low level human readable representation of the machine code instructions. Data retrieval. To obtain data values from the memory, the CPU sends a request to memory for one value at a time. Address communication. The CPU sends the memory location it needs data from over the address bus to the memory. Memory data transfer. Upon receiving an address, memory fetches the data from the address and sends it to the CPU via the data bus. Visual representation. The diagram showcases how the components communicate. CPU, memory, and input output. These are the main parts of the system. Control bus carries control signals. It regulates and synchronizes data transfer within the system. Address bus. It's a set of wires that carry memory addresses where the CPU wants to fetch or to store the data. Data bus carries the actual data between the memory and CPU. To put it simply, the Van Neumann architecture illustrates how a computer operates. The CPU fetches an instruction from the memory, decodes it, and executes it, and then possibly stores results back to the memory. The cycle repeats for each instruction. The various buses control, address, and data act as highways for the information to travel between the components. So this slide is presenting how a basic program can be executed on hardware, specifically a single core CPU. Let's break it down step by step to understand how the given code would be executed by the hardware. First step is instruction fetch. The CPU fetches the first instruction of the memory from the main memory. Address is not specified in this case. Second step, instruction decode. The fetched instruction is decoded to determine what action should be taken. In the given program, the first action is to declare variable integers, variable a, b, c, and average. Third one is the operand fetch. The CPU, knowing that it needs to calculate the average, fetches the values a, b, and c from memory addresses 512, 513, and 514 respectively. Execute. The CPU calculates the sum of a, b, and c and then divides the result by 3 to compute their average. This operation is done internally within the CPU's arithmetic logic unit ALU. The result stored. The computed integer average is then stored in an average variable which resides in the memory 600. Completion. The program returns 0, signaling the successful completion. This return statement informs the operating system that the program has finished its execution. The key takeaway here is to understand the basic flow of how a high level program, like the one written in C, gets translated into a series of steps that the hardware, specifically the CPU, can execute. This slide discusses hardware abstraction model. This is a simplified representation of how the computer hardware operates. Processor, the central component that crunches or processes instructions. For this example, we are considering single core unpipelined CPU. This means it executes instruction at time without overlapping different stages of multiple instructions. Memory, the storage component where data is held. When the processor needs to operate on some data or fetch an instruction, it sends an address to the memory. In response, the memory sends the corresponding data to the processor or receives data from the processor to the store. Address and data lines. These are communication channels between the processor and memory. Address. The processor uses this line to specify which location or address in memory it wants to access. Data. The line is used to send or receive actual data bits between the processor and memory. Now, this is a basic C program to calculate the average of three integers as shown previously. We'll talk about the hardware model diagram. This is a visual representation of how the processor and memory interacts. Processor sends an address to the memory when it wants to store or fetch data. The memory responds by sending or receiving data through the data line. The processor then processes or crunches the data. Memory stores the data bits. Understanding this abstraction is foundational for computer architecture. While real world computer systems are much more complex, this model provides a simplified view to grasp the basic interaction between a processor and memory. It's like a starting point from which more complex topics like pipelining, caching, and multi-core processing can be introduced. This slide is describing how a simple program in C is executed by hardware, more specifically, how the hardware handles the calculation average equals to a plus b plus c by 3. It's showcasing the basic interactions between the processor and memory during the calculation. This is the program, and now the steps of execution on hardware. Reading data. The processor fetches the value from the variable from a memory address 512. Another reading data. The processor then fetches the value of variable b from memory address 513. Adding. The processor adds the value of a and b together. Reading data. The processor fetches the value of variable c from the memory address 514. Adding. The result from step 3 is added to the value of c. Division. The sum of A, B, and C is divided by 3. Writing data. The result is then stored into memory address 600, corresponding to the average variable. This serves as an introduction to assembly language programming, highlighting the direct correspondence between high level language commands like C and multiple low level operations needed to carry out those commands. The operations performed by the processor highlighted in bold and data on which the operations are underlined. It is a clear example of how a single line of C code translates into multiple processor instructions, emphasizing the depth of operations that occur behind the scenes in hardware for even simple high level code. This slide delves into interaction between the processor and memory during the execution of a program. It is illustrating how high level programming commands can be translated into basic step by step hardware operations. Let's break it down so that you can easily understand. Main points: the processor memory interaction. The slide emphasizes understanding how the CPU and memory interacts when a program runs. Simple instruction. Physical hardware like the processor is designed to execute very basic instructions. Each simple task like reading from or adding two numbers is a separate instruction. Assembly language. The hardware level instructions are typically represented in assembly level language. Assembly language provides a set of human readable mnemonics to represent each low level operation and the hardware can perform. So each line is assembly corresponds to one specific operation on the hardware. The steps of execution on a hardware given the software program. The processor fetches data from the memory at location 512, then fetches the data from the memory location 513. Values are added from step 1 and 2. Processor fetches another piece of data from 514. The result from step 3 is added to step 4. Accumulated data value is divided by 3. Finally, the result is stored in the memory location 600. Now, the diagram provides a simplified view of the hardware. The processor fetches the data from memory using specific addresses. After processing the data, results can be stored back into memory. So the slide titled Visualizing Memory Contents give us a basic idea of how the memory storage works when a program is executed. The program is written in C and it's a simple program with the main function calculating the average of three integers a, b and c. The memory addresses are associated with these variables are provided in the comments in the code. A resides at 512, B resides at 513, C resides at 514, average resides at 600. The program calculates the average using the formula A plus B plus C and stores the result in AVG variable. Assumptions: the given integers value for the integers are A equals to 1, B equals to 2, C equals to 3. Hence the average calculated is 1 plus 2 plus 3 by 3, which equals to 2. Initial conditions: before the program begins execution, the processor is in an ideal state, meaning it isn't processing any data or executing any instruction. The memory contains initial values. Each address is a numbered label or a storage cell which contains initial data values. Now the visual representation: the processor and memory are depicted to show the interaction between them. Memory has various addresses starting at 0 and going upwards. Here the addresses 512, 513, 514 are highlighted. Contents of these addresses aren't shown. Now this slide read operation delves deeper into memory operations carried out by processor to compute the average of three variables a, b and c. Program as assumptions. It's the same program as before where a equals to 1, b equals to 2, c equals to 3. Result is stored in average. Now PC equals to program counter is a special purpose register that stores the address of the next instruction that processor will execute. It's a way for the CPU to keep track of its position in the program. Now the steps of the read operation. Processor reads the value from the memory address 512, reads the value of b from memory address 513 as the value of 1 and 2. Processor reads the value of c from 514, is added to the previous step, and then sum is divided by 3. Result is stored into the memory address 600. When a processor needs a variable's value, it requests the memory to send the data stored in a specific address. The address such as 512 is represented in bits when communicating with memory. For example, address 512 is represented as 000, 0100, 0000 in binary. Memory provides the data from the specified address without altering or erasing its original content. It's crucial to note that during a read operation, the original memory content remains unchanged. Only a copy of the data is sent to the processor. Let's summarize the slide. The slide showcases a basic operation that processor undergoes to execute a simple arithmetic operation and how data is read from and written to memory. This understanding is foundational when learning about how CPUs interact with memory in computer architecture. The slide second read operation contains from the previous slide focuses on second read operation. Program and assumptions, same program as before. A1, B2 and C and average as their respective addresses. Program counter. After the completion of instruction, the program counter increments, guiding the processor to the next operation. Steps of the second read operation. Processor reads from address 512. PC moves to the next step. Processor reads B from the address 513 where the value is 2. Binary representation, the address 513 is represented in binary, that is 000, 0100, 0001. The diagram depicts the processor reading the value 2 from memory address 513. In summary, the slide emphasizes the importance of program counter and illustrates how the processor reads the second variable from the memory during computation. The program calculates the average of three variables a1, b2, c and average have their respective memory addresses. Add operation sequence. After reading a and b, the processor now adds these two values. Diagram displays processor adding values 1 and 2. Binary representation. The values 000, 0 and 0000, for 1 and 00000000010 for 2 are now inside the processor. Operation specifics. The value must be in the processor to be operated upon. The result of the addition remains within the processor unless written out to the memory. Summary. The slide breaks down the addition step by step, emphasizing the data must be inside the processor for operations and results stay within the processor until saved to the memory. The processor reads value from the variable c which is 3 from the memory address 514. The diagram shows the data transfer from memory address 514 to the processor. Essentially, this is a visualization of the third data retrieval step in the program's operation to compute the average. Now I'll tell you how the processor performs the addition operation for the program. After reading values from memory addresses 512, 513 and 514, the processor adds these values. In this step, the processor is adding the value 3 from memory addresses 514 to the previously computed sum, which is 3 from a equals to 1 and b equals to 2. The diagram showcases the addition operation inside the processor with the result 6 from 3 plus 3. The key takeaway is that operations occur inside the processor, data is fetched one at a time from the memory. Let's talk about the slide title divide operation. After the values are read from the memory and summed up, the processor divides the sum, which is 6 from a equals to 1, b equals 2 and c equals 3 by 3. The diagram depicts this division operation inside the processor, resulting in 2 from 6 by 3. In summary, this slide shows the steps that processor takes to execute the divide operation, starting with reading data from memory, performing addition, dividing, and finally writing the result back to memory. Now in this slide, it shows how a simple program calculated result gets written to memory. The program calculates the average of three numbers a, b and c, that is 2. The slide depicts the series of operations the processor undergoes: reading data values from memory addresses, performing the addition operation, dividing the result by 3, writing the computed result to 600. When a processor is writing the result to memory, it sends the value 2 in binary to the data bus. Simultaneously sends the address 600 to the address bus. The memory, upon receiving this, overwrites the content of cell number 600 with value 2 in binary. This slide illustrates the state of memory and the processor after executing the program. When the program computes the average of values a, b and c, the average is 2. So post execution, the processor is idle. indicating the program has run its course. The memory now holds final values. Only change in memory is at address 600 where the computed average is stored. The diagram represents data in human readable form through actuality, memory stored in bits. The slide presents a problem where you need to choose the fastest hardware design for Netgear wireless security camera under a $20 budget. Now the options within the budget: processor 1 and memory 3, execution time 45 nanoseconds, processor 1 and memory 4, execution time 38 nanoseconds, processor 2 and processor and memory 3, execution time 47 nanoseconds. Recommendation is to choose one with memory 4 as is the fastest option within the budget at 38 nanoseconds.